All right, listeners, welcome back for another deep dive. Today we're going to be looking at topological superconductors.
Sounds fun.
Yeah, it's going to be a good one.
Yeah, I think so.
Okay, so you've probably heard of these things called topological superconductors, right?
Mm-hmm.
They're kind of weird materials,
Oh, yeah, definitely.
and people are really excited about them
Right.
because they might hold the key to some really, really crazy new technology,
Yeah, that's right.
like quantum computers. So we're going to try and unpack exactly why these materials are causing such a stir,
Okay.
and what makes them so special.
All right.
So maybe we could start with
Sure.
what is a topological superconductor?
Well, basically, it's a material that can conduct electricity with zero resistance,
Okay.
but it does it in a really weird way. So in a regular superconductor, the electrons flow through the bulk of the material,
Okay.
but in a topological superconductor, the electrons are confined to the surface.
Oh, so they're only on the surface?
Yeah, just on the surface.
Wow.
And they flow in these special protected pathways.
Okay, wait, so I'm picturing like a wire, and the electrons are like all bunched up on the outside of the wire?
Kind of, yeah. It's more like, imagine you have material
Okay.
and it has a special kind of shape,
Okay.
and the electrons are like stuck to this shape. They can only move along certain paths.
So it's like the shape of the material is dictating how the electrons flow.
Exactly.
Interesting.
Yeah, and these paths, they're what we call protected
Okay.
because they're really, really robust. Like you can try to disrupt them,
Mm-hmm.
but the electrons will just keep flowing.
Wow, so it's like they're immune to interference?
Yeah, pretty much.
Okay, but why are they called topological superconductors?
Well, that's because the protected pathways come from the topology of the
The
material.
topology.
Yeah, the shape, basically. You know how a donut and a coffee cup are topologically the same?
Wait, are you saying a donut and a coffee cup are the same thing?
No, 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 not the same thing.
Okay.
But they have the same topology. You can transform one into the other without cutting or gluing.
So like if you had a donut made out of clay,
Yeah,
you could mold it into a coffee cup.
exactly.
Okay, I kind of see that.
Yeah, and so in a topological superconductor,
Yeah.
the shape of the material creates these protected pathways that are really, really stable.
Because of the topology?
Yep,
Wow, okay, this is pretty mind-bending stuff.
it is, yeah.
But it's also really cool.
Oh, yeah, for sure.
Okay, so we've talked about protected pathways and topology. But there's another thing that's really important here. Majorana fermions.
Ah.
So what are these things?
Well, they're a type of quasi-particle,
Quasi-particle?
meaning they're not like a fundamental particle like an electron or a proton.
Okay.
They're more like an emergent phenomenon that behaves like a particle.
Okay.
And what makes them so special
Yeah?
is that they're their own antiparticle.
Wait, their own what?
Antiparticle. You know how every particle has an antiparticle?
Like matter and antimatter?
Yeah, exactly.
Okay.
Well, a Majorana fermion is its own antiparcel.
So it's like its own evil twin?
Haha, kind of.
That's so weird.
Yeah, it is.
Okay, but why is that important for quantum computing?
Well, because it means that information encoded in a Majorana fermion is really, really stable.
How so?
Well, if you try to disturb one part of the Majorana fermion,
Okay.
the information is still there in the other part.
So it's like having a backup copy.
Yeah, exactly.
That's amazing.
Yeah, that's pretty cool.
So that's why people are so excited about Majorana fermions, because they could be used to build really stable quantum computers,
Exactly.
and that could revolutionize all sorts of things,
Oh, yeah, absolutely.
like medicine and materials, science, and artificial intelligence. The possibilities are endless. Okay, so we've talked about the theory, but what about the practice? Like, how do you actually make a topological superconductor?
Well, it's not easy. It's really cutting-edge stuff. You need to create these very specific materials,
Okay,
and then you need to cool them down to extremely low temperatures,
like how low?
like close to absolute zero.
Wow, that's incredibly cold.
Yeah, it is.
So it's a real challenge,
Definitely.
but people are working on it.
Oh, yeah, there are lots of researchers all over the world who are trying to figure this out.
And they're making progress, so who knows, maybe one day we'll all have quantum computers in our pockets.
Maybe.
Okay, so to wrap things up, topological superconductors are really fascinating materials with the potential to revolutionize quantum computing and maybe even change the world. But there are still a lot of challenges to overcome. And it's going to take a lot of hard work and ingenuity to make these things a reality. So for all of you listeners out there, keep your ears open, because this is a field that's moving fast, and who knows what amazing breakthroughs are just around the corner. Thanks for tuning in to another deep dive, and we'll see you next time.